Problem gives us a maximum voltage and a maximum current, and also a frequency for the waveform. We're going to want to sketch the instantaneous voltage and instantaneous current, and we're going to want to draw what are called phasors for the voltage and current. So, first thing to do would be to number our axes. Here's 0 volts. This can be 2 volts and 4 volts. Now we want a sine wave that completes 1 cycle per second. So I'm going to use up the whole graph here. And we'll say that that time is 1 second. Notice that our peak voltage is plus 2.83 volts. Our peak in the negative direction will be negative 2.83 volts. Now let's draw our current. And this is in volts. This is going to be in amperes. Now when we're dealing with a source and a resistor, then the voltage across the resistor and the current in the resistor will be in phase. So they'll be in sync. They'll have the same basic shape, but different amplitudes. Our maximum current is 0.113 amps, and we have a negative 0.113 amps as well. And that takes 1 second to complete. This will be a half a second. What I'd like to do next is come up with a new axis here. Instead of the time axis, we'll focus on the angle. And this is going to be the phase angle. So in other words, what phase is the waveform in? So when we first start, if we're talking about a sine function, then we would be in a phase of 0. This will be a phase of pi over 2, a phase of pi, and 3 pi over 2 here. Notice how the current and the voltage are always in phase. And this is going to be reflected in our phasors as well. So how do the phasors work? Well, they're just going to be vector arrows that start from the center of the diagram and point toward the angle that we're at here. Now this can be my voltage phasor. Okay. And the phasor will circulate around. It's going to take a whole cycle for the phasor to work its way all the way around the circle. And it'll eventually come back to 0 degrees at the end. So this vector is going to move around the circle as time goes on, and it takes 1 second for that to occur. These are just snapshots of where it's located in time. All right, we'll label that the voltage. But we also want to include the current as well. Now for a source and a resistor, current and voltage are in phase. So what we want is we want just another vector here pointing in the same direction, and that can be the current vector. Notice that the current is a different magnitude than the voltage. The length of the vector represents its magnitude. The length of the voltage vector will be V max, which is 2.83 volts. And the length of the current vector will be I max, 0.113 amps. Let's find the period t, which is the time it takes for the phasor to make one complete revolution. It'll be 1 over f, which is 1 over 1 hertz, which is 1 second. Let's find the RMS voltage. It will be 2.83 volts over the square root of 2, which is 2 volts. Let's find the RMS current. And now let's fill out the following table for the instantaneous voltage at different times and the instantaneous current, and we'll also include the instantaneous power. So instantaneous power has a formula. To get the instantaneous power at a particular time, we just multiply the instantaneous voltage at that time times the instantaneous current at that time. Let's see, our theta in degrees will be 0. Pi over 4 is 45 degrees. This is 90 degrees, 135, and so on. Now our instantaneous voltage, if we look back at our graph, we can see that at time 0, we're at a voltage of 0. All right, so how will we find the instantaneous voltage at this phase angle? All right, so we'd better come up with a formula for our voltage. And it won't be too difficult to find. It'll be V of t equals V max sine of omega t, and we don't need a phase difference because this waveform clearly is in the normal phase. For sine, it starts at 0. So let's see. We're going to have V of t equals 2.83 sine of 2 pi f t. All right, it looks like our function is 2.83 sine of 2 pi times t. All right, so we can plug in the different times. But what if we wanted our function in terms of theta instead? Well, in that case, we don't have to use t at all, because omega t is an angle. So it'll be 2.83 sine of theta. All right. For the current, it's going to be similar. I of theta, 0.113 sine theta. So let's use those formulas to complete the table. Okay. For that, I get 2 volts. Here we'll have 2.83 volts. We'll be back to 2 volts. Here we'll have 0. When we use a theta of 225, we're going to get negative 2 volts, negative 2.83 volts, and negative 2 volts. So we can see how it's sinusoidally oscillating here. For the current, we'll use a similar formula, 0.113 sine of 45. That's going to be 0.08 amps. Let's see, then we'll have 0.113, 0.080, negative 0.08, and you can see the pattern here. All we're doing is we're getting values that are on these graphs. Now let's find the instantaneous power. How do we do that? Well, all we have to do is multiply the instantaneous voltage times the instantaneous current, and that will give us the instantaneous power in watts. So it's going to be 0 when we're in phase 0. When we get to pi over 4, our power is going to be 0.16 watts. But when we get to that peak, our power grows to 0.32 watts. And you'll see the pattern here. One thing that's interesting that happens here, though, when we multiply a negative voltage times a negative current, we still get a positive power being dissipated by the bulb. And that should make sense, seeing as how a resistor will be dissipating positive power throughout time. So the maximum power that is dissipated here is found by multiplying V max times I max. Okay, so that'll be 2.83 volts, 0.113 amps, 0.32 watts. But when we find the average power, we can use this formula. VRMS times IRMS. So that'll be 2 volts, 0.08 amps, 0.16 watts. Let's take our graphs to Desmos and see what they look like side by side. All right, first of all, we have the voltage function. our cycle should have a maximum of 2.83 volts, which it does. It should complete its full cycle in 1 second, so this looks great. And let's put in our current function as well. Alright, that's the current in our circuit. It's going forward, and then it's stopping, and then going backward, and stopping, and going forward, and it just keeps oscillating like that. Now let's do something new. Let's find the power function. Power as a function of time will be given by the product of the voltage times the current. And look what it does. The power for an AC circuit involving just a resistor and a source is going to always be 0 or positive, never negative. We dissipate the most power when the most current is flowing and when the voltage is highest. We'll dissipate 0 power, though, when the voltage becomes 0 and the current ceases. But even when the current goes backward, we still dissipate that same amount of power as we did when the current was going forward.